In our contribution titled Scintilla, Simulating Combustible Vegetation for Wildfires, we propose a novel method for simulating wildfires. Wildfires are disastrous natural phenomena that ravage communities and ecosystems alike. A wildfire is the uncontrolled and often unpredictable combustion of vegetation that not only includes trees and shrubs, but also other types of fuel such as grass, duff, dead leaves and needles. Surface wildfires can be relatively harmless phenomena when their progression is constrained to the forest floor. Once wildfires start torching trees and progressing vertically, a dangerous crown fire can be initiated. The most severe wildfires can turn into a blazing inferno that consumes all the biomass in a forest. In a mixed deciduous and coniferous forest, a wildfire may primarily combust drier trees, resulting in active crown fires that leave some trees alive. Active crown fires are the result of vertical flame spread, which occurs as a result of a vegetation distribution of unequal height. Vegetation management deals with removing vegetation in the middle layer of a forest, which may severely reduce the risk of a crown fire emerging. Our novel model of wildfires can plausibly simulate the combustion of vegetation in a number of different biomes. For example, here we set a savanna scene ablaze composed of grass, shrubs and trees. The grass and shrubs catch immediately on fire, with the fire line progressing further through the scene, setting everything on fire in its wake. When a tropical rainforest burns, it releases a huge amount of vapor into the air due to the increased amount in biomass. In this case, the taller trees of the wetter climate do not catch on fire, with the fire line progressing close to the ground. Our model takes into account not only the spatial distribution of fuel, but also its disposition to combust, referred to as fuel moisture. Wildfire progression and behavior is largely dependent on the distribution of fuel moisture. Here we show 3 different progressions of wildfires in a shrubland scene caused by varied fuel moisture distribution. In addition to complex fuel distribution, our model simulates the generation and transport of embers during a wildfire, which may result in the ignition of new fire sources ahead of the main fire line. Our realistic wildfire simulations can produce fire line progressions that behave similarly to ones encountered in the real world. In our paper, we have assessed the similarity of our simulations to a controlled burn experiment from the scientific literature. Due to the use of efficient representations for plant shape, we can interactively simulate wildfires in scenes of hundreds of thousands of plants. Here, a grassland fire reaches the edge of a mixed forest at the foot of a mountain. It turns into an active crown fire, burning down the drier fir trees. As the temperature increases due to the heat release of the burning trees, the wildfire becomes more destructive. Eventually, embers are formed during tree combustion, which, advected by the wind, land in new places to cause new fire spots. Finally, as the fuel distribution becomes sparser higher up the mountainside, the wildfire wanes and reveals the damage caused to the ecosystem. Our complex representation of vegetation, coupled with an efficient combustion model, allows the interactive exploration of wildfire phenomena at unprecedented detail.